So the four countries driving this effort navigated through the divisive Cold War politics of the time and found a way to work together that would benefit the whole world. The result? These two spacecraft, with some adjustments, would soon become the eyes in the sky that would make the program possible. Cospas Sarsat is nothing if not thorough. For example, here is the very first document called the Cospas Sarsat Implementation Plan. It was developed in 1980. It is the formula for designing, developing, and building the entire system. It showed the outline for satellite payloads, 121.5 and 406 MHz channels, and beacon messages and MCC data distribution plans, and schedules for when things will be developed and built and tested. Although all of this is over 40 years old, most of the material in this book is still in use today. This plan led to the development of new equipment by all the parties during 1980 and 81. Teams of scientists and engineers in both government and industry worked together to design, build, and test various elements of the program. This step was needed to demonstrate and evaluate every aspect of this experimental system. We are here at a typical test site that all the parties would have had in the 1980s. In this case, we are at Shirley's Bay in Canada, where the original Sarsat payload was designed and tested, with the help not only of engineers from CRC, but also NASA and CNES, the French space agency. How do I know that? I was there. It was great that digital beacon technology already existed, thanks to the French Argo system, so it was just a matter of adapting it to meet our SAR requirements.
So that new system with a digital approach using the 406 MHz was considered to be needed. Therefore, what NASA was telling us, we would like you to focus on the new system at 406 with a more advanced technology based on beacons which have a quartz on board, which have a stable frequency standard on board, and therefore the Doppler processing of the signal allows for a much more accurate position location.
The development of the 406 digital beacon accelerated rapidly at this time, shrinking in size from the equivalent of a small bar fridge to a microwave oven, to the familiar handheld model shape still in use today. It's important to remember what made the 406 so vital to the future of Cospas Sarsat.
The 121.243 signal was just a swept tone signal. There was nothing about registration, and it wasn't designed for satellite detection and things like that. So the key things about the 406 signal was it was a more powerful signal, so more reliable in terms of satellite detection, but more importantly, it was a digital message that contained information about the owner of the beacon. So now if you have a false alert, in theory you could look up the owner of the beacon in a registration database and call them up. Or call up their emergency contact. So that was a significant improvement in terms of trying to reduce false alerts. One of the key things that 406 would hopefully do for you.
Let's compare the components that make up an analog 121.5 MHz beacon to its digital successor, the 406 MHz beacon. As you can see, the digital model is much more complex, reflecting the more robust information it is designed to provide. By 1982, all the equipment was ready to be tested as a complete system. In Canada's case, the end-to-end test at CRC included both types of beacons, a LUT built by Cal Corporation, and a satellite payload built by Spar Aerospace. In the US, similar testing was going on at NASA and TSI. including modifications to the NOAA Tyros satellites in order to accommodate the new SAR payloads and the transmit and receive antennas. France was finalizing the 406 SAR processor, which would be connected to the Canadian repeater. Similar work was going on in the Soviet Union.
Потому что, когда мы начали разрабатывать свою аппаратуру, это был 78 год начала, и до запуска первого спутника было 4 года, поскольку он был запущен в 1982 году. Вот. Было время, когда и западная аппаратура, в том числе и микросхема, и процессоры, это все могли поставляться, и мы могли, и получали мы из западных стран, ну, в основном из Америки.
It was important that Cospas and Sarsat systems be compatible, even though the Soviets' work on their Cosmos satellites had to be independent, of course, from the other parties, due to some restrictions on technology transfer.
Для того, чтобы обе системы работали одновременно радиобуями многих стран, требовалось одно – обеспечение совместимости. Поэтому этой работе было особое внимание. Я был заместителем технического руководителя именно по этой проблеме. То есть выпускались документы, в которых сигналы и сообщения строго расписывались до бит и до вольт включительно. И обеспечение совместимости в теории и реализовано на практике, оно и обеспечивает работу этих систем после запуска их на орбиту.
Pre-launch validation tests were carried out. In the end, some U.S. hardware exchanges, with permission from the State Department, were essential. Given that the future of the system hinged on the successful outcome of these tests, Bernie Trudell made sure that permission was granted, although one of the handoffs did not quite go as planned.
The downlink polarization on the Cospas was different from Sarsat. So Bernie, he said, we'll get the right kind of antenna so that the Soviets could test and make sure they were getting stuff off of our satellite. It got all late, and then we were going to Ottawa for a meeting. So he said, well, take the antenna with you. I said, you should have given it to the State Department. They could have put it in some sort of dispatch package, and passed through customs. So I actually got the counter. The customs took it away from me, actually. So I get to the meeting, and Bernie says, where's the antenna? I said, customs took it away from me. I said, look, I'm going to talk to the head of the Canadian delegation and see if he can't go get it back. Bernie actually went with me. And about 3-4 days later, the antenna showed up, and then we gave it to the Russians. And I don't know how they got it out, but my guess is it went through their normal diplomacy situation.
Not every challenge was resolved so easily. A major hiccup surfaced while testing the first SAR payload on the NOAA satellite at the RCA facility in New Jersey.
RCA integrated the Canadian instrument onto the NOAA-E satellite at the Astra plant in New Jersey. CRC technicians conducted a series of tests on the instrument, which duplicated tests done at the factory level at Spar Aerospace in Montreal. After returning to CRC, one of the technicians commented that the test of the 121.5 MHz receiver sensitivity produced a result that was significantly worse than the factory level result. This indicated the possibility of a strong electromagnetic interference EMI problem.
The NOAA weather instruments were unaffected, but the very sensitive SAR receiver experienced strong broadband noise and interference spikes coming in via the antenna from an unknown source.
RCA and NASA initially speculated that the EMI tests failed due to the proximity to New York City airports, affecting the 121.5 MHz aeronautical band. I did not agree with that assessment.
There was much back and forth with the NASA Anomaly Review Board as to the potential cause of the failure. Canada argued that because the test had been done in an unshielded environment, a retest in a radio frequency, RF, shielded thermal vacuum chamber was needed.
We knew that if this was not done, proving the ability of the SAR repeater to detect 121.5 megahertz distress signals would be in jeopardy. NASA management finally authorized a retest. The results confirmed what we suspected. The interference came from other equipment on the satellite itself. In other words, each wiring harness was acting like a transmitting antenna that emitted signals that would drown out any ELT distress signals.
After extensive investigation, the solution to this problem turned out to be simple, but time-consuming. RCA had to modify most of the wiring harnesses on the spacecraft with shielded and ferrite-beaded cables, as well as install conductive boots on each connector to suppress the radiated interference. And that's how it's done. When we ran the test again, what do you know? No interference. Solving this problem meant the Sarsat mission was saved. But this setback would delay the Sarsat-1 launch by almost a year. On a positive note, RCA stated that the experience gained in this investigation led to the reduction of radiated EMI in future satellite designs. Although it was planned that Sarsat was to launch first, but given the delays due to technical issues, it was agreed by all parties that Cospas should launch when ready. Even the Soviet effort was not without problems.
We were in Moscow for a Cospas Sarsat coordinating group meeting. And the first Cospas payload had been launched a few months before, but didn't work. Because we had received the signal in our LUTs, the data was not usable. So at the opening of the meeting of the Cospas Sarsat coordinating group, Yuri Zurabov, who was the head of the Soviet delegation, welcomed us and said, well, you probably have noticed that the first Cospas payload launch does not work properly. Well, I am happy to tell you that we have been able to understand the problem, to fix the problem, and we have launched a new one. And this was typical of the way the Soviets was working at the time. We had not yet launched the first Sarsat payload, which came only the following year, in '83.
With the technical problems suffered earlier now in the rearview mirror, the Cospas Sarsat Coordinating Group confirmed system readiness on April 16, 1982, for launch of the first satellites carrying SAR payloads. This would be the beginning of the D&E, demonstration and evaluation phase of the project. The four parties were thrilled.
Техническая аппаратура, были созданы наземные станции приема спутниковой аварийной информации, а также центры системы Cospas Sarsat.
Yes, I agree with Mr. Zurabov's assessment. That indeed, this meeting has been very successful.
We in Canada have the same general problem that the Soviet Union and France and the United States.
У нас в Канаде те же проблемы, что и у вас, говорит господин Маккинон. Также терпят бедствия суда вдали от берегов. Также случаются вынужденные посадки самолетов в глухих районах. И мы возлагаем большие надежды на эту систему.
I would like to say also that we are very happy because we are slowly other countries.
Я счастлив, говорит представитель Франции господин Браше, что к этой системе проявляют интерес уже очень многие страны, и она обещает стать надежным помощником для мирового сообщества.
Мы ожидаем, что в ближайшее время, в начале лета, состоится запуск первого космического аппарата, который будет работать с этой системой.
The technical development of the system was fairly smooth, and there was a good cooperating spirit between the various participants.
With the impending launch of Cospas-1, we moved into a final phase, testing a satellite's ability to receive distress beacon signals under actual space conditions. To accomplish this, ground station equipment had to be in place, as well as personnel to monitor the satellite data. In Canada, Ted King, no relation, was one of the first Mission Control Center operators to come on board in 1981.
I was a major at the time that this Sarsat project started up, and I was assigned to work specifically with the CMC during the developmental and evaluation phase. That was physically located here at RCC Trenton. I stayed in that job once things got rolling until 1991.
On June 30th, 1982, Cosmos 1383 was launched from Plesetsk, Russia. It would be the first Cospas satellite to carry search and rescue instruments as part of its payload.
Он выведен на круговую полярную орбиту с высотой 1000 километров и позволяет начинать проходить летные испытания всей системы, включая наземный комплекс и центры управления и всю остальную часть системы. В течение 70 дней шли с успехом летные испытания, определялись параметры системы.
2 months later, on September 1st, the Soviets declared it ready for D&E testing. Within days, this experiment would chalk up its first success. September 9th, 1982, a single-engine Cessna piloted by John Ziegelheim flew a search pattern over the Rocky Mountains in British Columbia, Canada. He and his 2 passengers were searching for an aircraft that had vanished more than 7 weeks before.
A father at a church, his son went missing out there around Dease Lake, and so one of my students who goes to that church wanted to see if we could go out there with the father, and they hadn't found him in a week or so, and he thought, well, maybe if I just go see where he was flying, I might understand it better. So off we went. We got to Dease Lake, no problem, and then we went flying around, and it was time to return home. We ran into some bad weather, but we knew that if we'd gone down this valley, we would get down to the airport. And unfortunately, we misread the map and made the right turn too early, and there was no end out of that canyon. And that's when we went into the trees. I had a broken leg. Gary had the broken ribs and wrist and nose. And the father was okay. And we set up tent, and we thought, well, okay, we did file a flight plan, so they do know we're missing. They just don't know where we are because we had changed course.
And they'd gone out and done an initial search without any luck when Ziegelheim was reported overdue. So I was called in to see if we could use the satellite system to help. So I came and got it set up to track satellite passes in the western fringes, which it was. We only had the one tracking station operating at that time in Ottawa. So to pick up something in British Columbia was sort of at the extreme limits of the system.
We had the ELT with us. It was bolted to the airplane, but I mean, it was in great shape. It was in the tail, so it survived fantastic. The antenna was sticking up. And so what we thought we'd do is we take the, we could get the ELT out, but we couldn't get the antenna out. And we thought that was pretty important. So I got up on top of the airplane with an axe, and I thought, well, I'll cut around it, and then I can take the whole antenna out of the airplane. Well, I took a couple of whacks at the fuselage, and the antenna went flying. And we thought, well, that wasn't good, but it's out. So we took it with us, and then turned it on that night.
So I came in, checked the satellite schedule. We had some prediction software which we used, took a look at what passes were suitable, made sure that the tracking station was scheduled to take those passes. Well, it wasn't a difficult task because we only had the Russian satellite at the time, but there were long gaps in between, but made sure everything was working, the communications and so on. And of course, when the pass occurred in the middle of the night, the data was automatically forwarded to RCC Victoria, and they reacted to it, I believe it was the next morning.
Okay guys, we've just been tasked by RCC to search for a aircraft in distress.
That morning we got a hit. The satellite picked it up, and we proceeded out to the lat and long they give us. And we're approximately about 10 miles away from the crash site. And we picked up a DLT, and then we circled around, and that's I spotted the tent and the Casleys. And that's when we made the decision that we're going in.
The next morning, bright, beautiful, clear day, and we heard an airplane come by, and they were circling. The guys are out there, and they're telling me what's going on, and they're going, "There's a plane here," and it's a big Buffalo, so they're going like, "Yeah, somebody's found us." Well, that's when they came back and dropped the paratroopers in.
So we landed right by where the survivors were, and it was a matter of feet. We were right on target, both of us. There was 3 casualties. We had fractures of the lower limbs, broken ribs, facial lacerations, and shock. So they were in bad shape. If it wasn't for the Cospas Sarsat satellite, it would have took us maybe anywhere from 3 to 4 days, maybe a week to find the survivors. And if we had waited that long, the type of injuries they did have, there probably would have been some deaths. You know, they wouldn't have made it.
They evacuated us out of there with the helicopter and took us out to a waiting airplane in the hospital. And we made it home. And we still hadn't known how we got rescued until we got to the Air Force Base before the hospital. And somebody said, well, the satellite found you. We're like, what satellite? There's no such thing. It's a radio beacon. And well, I don't know, something happened. So we didn't know the whole story until later. You know, as it turned out, it was our good fortune that you turned the machine on that night and picked us up right away. And 40 years later, here I am, still alive.
Через 70 дней после запуска пресса мировая взорвалась сообщением о том, что советский спутник спас экипаж канадского самолета Cessna-172. Это, конечно, окрылило всех тех, кто занимался разработкой системы Cospas у нас, так как это означало, что сработала эффективно вся система целиком.
Man, I'm glad those guys had the foresight to put together something like that. I mean, like 40 years later, how many people it's helped? It's just an unbelievable project.
I think when you look at going to a meeting with 40 countries or thereabouts sitting at the table, yes, history was made. Because if we didn't have these early successes, it would have been, I say, probably not budgeted or funded, gone down the tubes like many other projects.
On October 10th, 1982, 1 month after SAR-Ziegelheim, a trimaran, the Gonzo, sailing from Maine to England with 3 crew on board, encountered heavy seas and capsized about 500 kilometers southeast of Cape Cod. Fortunately, they had a 121.5 EPIRB, which provided the distress alert. Based on that alert, the U.S. LUT, using the Doppler shift, was able to calculate a location. The Gonzo was both the first satellite-assisted maritime rescue and the U.S. Coast Guard's first recorded save using Cospas Sarsat data. Following that, satellite-detected 121.5 distress beacon rescues occurred on average once a week. Over the next 2 years, extensive demonstration and evaluation testing continued, as did the number of rescues, even though the system was still in test phase. In early 1983, 2 more satellites, SARSAT-1 and Cospas-2, were launched, which reduced waiting time for a satellite to come into view of an active distress event. In 1984, a second SARSAT satellite was launched. Having those 2 SARSAT satellites as part of the U.S. commitment to the MOU ended up proving to be very useful to one of our partners, NOAA. In 1984, a hearing was convened by the U.S. House of Representatives Science and Technology Committee to decide whether to cut funding for NOAA's second LEO weather satellite. NOAA reminded the committee that the U.S. had committed to maintain 2 SARSAT-equipped satellites in order to be compliant with the Cospas Sarsat MOU. You could say that the SAR payload came to NOAA's rescue. Having 2 SARSAT satellites in orbit would continue for the next 40 years. Following the early success of the project and the budget approval in the U.S. for 2 NOAA weather satellites, a new 5-year MOU was signed in late 1984 to allow the system to transition from experimental to operational under the new Cospas Sarsat Steering Committee. The 4 founding countries, as well as a few other interested participants, including Norway and the United Kingdom, conducted tests using 121.5 and 406 beacons in various environments and a variety of temperatures and elevations on land and sea. Since the MCCs were physically embedded at RCC sites, this new technology intrigued RCC operators. But at the outset, they were hesitant about putting complete trust in the system.
We told the RCCs about this great new aid to their system, and of course they accepted it as that. However, it became somewhat of a problem in detecting false alerts. So we tried to do this without losing their enthusiasm for the Cospas Sarsat system. And so it was always a constant battle to show why we were detecting false signals coming in from the LUTs. And it was very difficult to explain about sidebands and interferers and pizza ovens and all the other reasons which the RCCs really didn't care about. They wanted the actual beacons to be coming in. I remember that we told them that anytime we received a 406 message, it was going to be a real beacon. It was a digital message. It was going to be real. It was going to be out there. And you know what? We're still fighting a problem of false alerts, system anomalies. So there's still a small amount of uncertainty within the RCCs. But with the 406, it has improved their operation quite a bit.
The accumulated saves during this D&E period gave the system credibility with RCCs and helped them gain confidence in the system. In 1985, the technical and operational parameters were evaluated, showing that the 121.5 and 406 systems both exceeded expectations and in fact proved it, with the 121.5 system providing major support in the rescue of 473 people in 194 real distress incidents in under 3 years. The demonstration and evaluation phase also proved useful as they gave the engineers real-time data regarding the limits of the system and reinforced the need for at least 4 satellites to effectively provide timely rescue detection and location data. By 1986, now that the parties had developed the technical aspects of the system, they soon realized that a data distribution plan was key to disseminating distress alert data around the world.
I remember working on developing the data distribution plan, which had to do with how we were going to distribute with a small number of MCCs data around the world. Who would distribute all of this data to? Because we only have 4 MCCs in the world. How are we going to get it to the areas in which the alert was located? So there was quite a bit of work to even convince the MCCs, the MCC operators, that they had to do this, because there was some feeling in the countries that, according to IMO, if you're the first person to receive the information, then you're responsible for the processing of that information. And MCCs didn't want to accept that responsibility of being responsible for conducting the search and rescue, contacting the foreign search and rescue outfits to talk to somebody. So we had to develop a way, basically a worldwide data distribution system. So that's quite a challenge. And I think Cospas Sarsat today still has the only or the best data distribution system to provide alert data worldwide.
Running parallel to that, in April 1986, the first 406 beacon technical specification was approved. Manufacturers began designing, building, and testing 406 beacons, starting with EPIRBs. Each new model had to be tested by an accepted laboratory and type approved by Cospas Sarsat once the results were submitted.
The 406 signal started coming into being in the early 80s, and the company developed let's call it a black box version of a 406, early 406 transmitter, which they were supplying to adventurous people to track what they were doing. In particular, Richard Branson, on all of his escapades, either in balloons or when he was trying to go speedboating across the Atlantic, he had these prototype devices with him as well. And then in 1988, the UK government decided that it was going to mandate this new device called an EPIRB that nobody had absolutely any idea what it was on fishing vessels in the UK. And suddenly there was a market for this box of tricks that would only be made in prototypes until now. They got me back on board to project manage that program. I had no idea what an EPIRB was. Nobody had any idea what it should look like. Fortunately, in Norway, they'd been already using maritime versions of 121.5 megahertz beacons, and so we looked at what Norway was doing to produce our first 406 megahertz beacon, which was, you know, sort of this tall and this diameter, and had 10 D-cell batteries in the base of it to power it, 5 printed circuit boards. It was a beast. When we first started with EPIRBs, most of them had gravity switches. So you would mount your EPIRB upside down in the bracket, and then when it came out of the bracket, it turned up the right way and that activated it. What we found was that you got an awful lot of false alerts because people took them out of the bracket to test them, or out of the bracket because they wanted to paint the wall that the bracket was mounted on or whatever. And that created all these false alerts. So while it seemed like a good idea initially, it was actually a very bad idea.
The beacons became available to the general public 1 year later. Jotron, based in Norway, was the first 406 beacon to be approved.
We built this EPIRB, which was intended to be the very first one that was approved. Unfortunately, we missed that by a day to Jotron, who have tax certificate number 1. And we missed out because there was an error in our paperwork, which the Secretariat rejected. And so we ended up with tax certificate number 2 a day later.
And that wasn't somebody named Jim King that did that?
It might well have been somebody named Jim King, yes.
In the next 3 years, there were over 50 different models being manufactured in at least half a dozen countries.
In those early days, the beacons were not as reliable as they are nowadays, and therefore there was a fairly high turnover in terms of manufacturers bringing out new beacon models, price changes and things that meant that the market was updating itself.
From the outset, it was a requirement that each 406 beacon owner had to register his beacon with his national administration.
Because the beacon is registered, they can make some phone calls, and they can find all the false alerts.
The final step to achieve global status was to formalize the program on a long-term basis. The goal was to gain acceptance by IMO and ICAO, which required a formal 15-year commitment to maintain system operations both on the ground and in space to serve the maritime and aviation communities, as well as terrestrial usage, depending on future beacon development.
The cooperation was enhanced in 1988 by the signing of an intergovernmental program agreement, the International Cospas Sarsat Program Agreement, by the same 4 parties, which established the satellite system on an international basis as an international organization and allowed other states to join the program, to become associated with the program.
The agreement was signed on July 1st, 1988 in Paris. That established the system for the long term, created a council to oversee the program, a joint committee to address technical and operational matters, and a secretariat staff to manage Cospas Sarsat. 2 of the most important tenets of the agreement were incorporated at the outset and have remained a commitment right to the present.
Well, the International Cospas Sarsat Agreement is really the equivalent of a treaty between the various states, which guarantees the continuity of the service and its availability to all states without discrimination and at no cost to the end user in distress.
The initial secretariat, located at Inmarsat in London, started out with a staff of 2. How do I know? I was there. Over the next few years, efforts were made by IMO and ICAO, as well as industry, to encourage other countries to participate in the management and operation of this new global system. By the end of the 80s, several countries had already signed on and installed LUTs and MCCs to improve coverage in their SAR areas of responsibility. Use of distress beacons and the number of lives saved grew exponentially during this period.
A number of countries joined the cooperation before we signed the intergovernmental agreement. That is the case in particular for Norway and UK.
Knowing who owned the distress beacon, the country of registry, as well as vessel or aircraft identification was the major advantage of 406 beacons to SAR authorities, since they could count on the distress signal being real and weed out most false alerts with a simple phone call. In a swimming pool? Really? At which motel? New ideas on how to improve the 406 system were coming fast and furious. A proposal by NASA to add a second satellite constellation was gaining traction. Much of the technology was already in place, and although there were some limitations, the resulting data would speed up the process profoundly, from hours to minutes.